Hello girls, welcome to Digital Learning Day number 2. Today we're going to continue looking at sine and cosine graphs and their equations. Last class we concentrated more on what the graphs look like and how they differ depending on changes to the equation. Today we're going to look at the equation and what that would do to the graphs. And again, Ms. Holman and I are both aware that this is a lot to look at digitally for 2 days. So we will definitely review all of this next class and make sure everyone's up to speed. But in the meantime, do the best you can in following this video. Pause it when you need to fill in the notes, and just have a general understanding of what we're referring to. And again, we'll go over it hopefully Thursday. Hopefully we'll all be back together again at school. So when we first graphed sine and cosine, we looked at just the original functions, just sine of x and cosine of x. Then yesterday we looked at what the graphs look like as you add numbers. Today we're going to look at how putting numbers in different locations of an equation change the graph. So as we saw yesterday, there are 4 different positions of a trigonometric function that you can add numbers or add value to. We're going to look at what each of those are called and what they do to the graph. For example, if we put a value in the position right in front of the actual sine or cosine term, that is called amplitude. And that affects the height of the graph. It represents half the distance between the max and min values. So amplitude is going to make the graph taller or shorter depending on the value of A. If we put a value inside the function, parentheses, right in front of the x, that is the b value in this equation, and it affects the period of the graph. And just like we saw when we did our Twizzler activity, the definition of period is the degrees or radians required to complete one cycle of the given function. So as we change those values in front of the x, that will change how much of the how fast we complete one cycle or how slow we complete one cycle. Or another way to think about it is how much of the cycle actually gets finished within 0 to 2 pi. And again, we'll look at that with some examples here in a second. If we add values in the C position, which is actually adding or subtracting inside the parentheses, that represents what we call, that represents what we call a horizontal translation, and it is a left or right shift of the parent graph. And again, we'll see some examples here in just a second. As we add values to the D position, or outside the parentheses, and we add or subtract values, that represents a vertical translation, and that shifts the graph up or down. So it represents an up or down shift of the parent graph. So let's look at some of these examples. If we go to the next page, on this page we're going to look at we're going to create a chart with the different changes to the equations and see what that actually does to the graph as we take one change at a time. For example, this top line here, we are looking at y equals sine of x. And this graph represents y equals sine of x. Again, it looks just like what we did with the Twizzlers and the spaghetti, just kind of a sideways S. Now, if we change the equation by adding a d, then the equation looks like this. Y equals sine of x plus 2. What that does to the graph is if we let this blue line represent just sine of x, then sine of x plus 2 shifts it up 2 units. So it's no longer centered around the x-axis, but it is up 2 units. Again, still has its sideways S, it's just been shifted upward. If we were to add a value of d but subtract, then the equation would look like this, sine of x minus 2. And the graph, again, if you picture it as having, this is sine of y of x, or y equals sine of x. And minus 2 just shifts it down 2 units. So again, still the sideways S, but instead of being centered on the x-axis, it's shifted down. If we add a c value to the equation, such as sine of x plus 45, again, our definition of the c value is a horizontal shift, so it shifts it left or right. Adding a positive c value actually shifts it to the left. So again, if we think of this as the sine of x equation, shifting it to the left 45 degrees, or would take it from being at the origin, the y-intercept at the origin, and it would shift it to the left. So it kind of places it off center. So it hits the x-axis more into the negative values. The next entry looks at adding a negative c, such as sine of x minus 30, and again, a negative c value will shift the graph to the right, c units. So again, if we use this blue line as representing, well, if I can grab it here, sine of x, then minus 30 degrees means the whole graph will shift over about 30 degrees. So again, it's no longer hitting the x-axis at the origin, it's shifting over. Sometimes the horizontal shifts are some of the hardest to identify. If we look at the a value, which we call amplitude, that is multiplying a number by the function. So for instance, we have 3 times sine of x. So now we have an amplitude, so a equals 3 gives us an amplitude of 3. So what that means is that we can think of that as a vertical stretch, or making the graph taller by 3 units, or by a factor of 3. So rather than just going up 1 and down 1 like the original graph did, excuse me, let's see. So again, this blue line represents just what sine of x looks like. 3 sine of x means instead of just going up to 1 and down to 1, it is now going up to 3 and down to negative 3. So it is stretching it by a factor of 3. Again, normally if you don't have an a value, you assume a is 1, so it goes up to 1, down to negative 1, and a of 3 goes up to 3, down to negative 3. If we have an a value that is a fraction, and instead of making it taller, it makes it shorter. For example, if we have an a value of 1/2, it is a vertical compression, or makes the function shorter. For example, again, this is sine of x, and it goes up to 1, down to negative 1. If a is 1/2, then it is now going just up to 1/2 and down to negative 1/2. So again, it makes it flatter, it compresses it. If we look at the b value, which we call the period, affecting the period, sine of 2x means the function cycles through b times as quickly. So again, sorry about this, a little typo in the notes. This should be b times as quickly. So if our b here is 2, it means it cycles 2 times as quickly. So instead of getting through one cycle from 0 to 2 pi, this is getting through 2. For instance, if we bring down our y equals sine of x, it goes up and down 1 time from 0 to 2 pi. But with a b equal to 2, it is going up and down twice from 0 to 2 pi. So it's going up and down, up and down. So it's moving faster, is one way to think about it. If we have a b value less than 1, it's a fraction, so it means it's going, again, b times as quickly, but with it being a fraction, it means it's actually moving slower. So it's going half as quick, is one way to think about it. So rather than going up and down once from 0 to 2 pi, it is only going, it's only going up and then falling, and it's not getting to the second half of the cycle because it is only moving half as fast. So it's only getting half of the period, half of the rotation accomplished. Putting a negative in front of the fraction as a negative sine of x simply flips the function. So rather than starting up and going down, it is flipped and is starting down and then going up. So that's what the negative sign does in front. So what we're going to, how we're going to apply this and practice it is actually looking at some graphs and trying to match the equation to the graph by using this chart and anticipating what each value in the equation represents. So for instance, if we go to the next slide, if we want to match these equations to the graph, I'm going to get you guys started here, and then I'd like you to try it and then come back to the pause the video after we go through an example and then try to match them up, come back and see how you did. But as an example, if we look at A, the A equation here is 3 sine 3 of x. So from what the notes we just took, with it having a 3 on the outside, we expect it to have an amplitude of 3, so we expect it to be going up 3 and down to negative 3. And with the 3 on the multiplied by the x, that tells us that it should be moving 3 times as fast. So instead of just going up once and down once, it should be going 3 times. So actually, when we think about those changes, we can look actually at number 5 here and see that this graph matches this equation. Because again, it's going up to 3 and down to negative 3 as it cycles, and it's also cycling once, twice, 3 times. So we know that A matches this number 5. If we look at another one, let's go ahead and look at B, 3 cosine of x. So again, here we expect the normal cosine graph, which we know is kind of like an upside down C, but instead of just going starting up at 1 and going down to negative 1, we expect it to be going up to 3 and down to negative 3. So if we look up at our graphs, we can see that that would match this one. Because again, it's just the normal cosine graph, where it's just like an upside down C, but it's starting up at positive 3 and going down to negative 3. So again, that just the amplitude is changing. So this graph 3 would match with the equation B. So now what I'd like you to do is pause the video now and try to match the rest on your own. And then after you've paused, come back and I will show you the answers. Okay, here are the final answers for the matching activity. Again, number 1, the first graph is F, and it represents sine of 3x. So again, it still has the same amplitude, it's just going up 1 and down 1. It's still centered across the x-axis. However, the 3x represents the fact that it is going through 3 cycles from 0 to 2 pi. Number 2, E, represents the equation sine equals 0.5 of x. So again, that represents how fast or slow it moves. So again, from 0 to 2 pi, this is only getting through half of the sine cycle. So instead of going up and down within that x values, it is only going up. Number 3, we already talked about, is representing B. Number 4 is D, and again, the D equation is 0.5x. So again, it's the normal 0.5 cosine of x. So it's the normal cosine graph, But instead of going up to 1 and down to -1, it is just going up to 1/2 and down to -1/2. 5 we talked about as A, and the last one is C. And again, we can look at this one. The equation is 3 sine of x plus 3. So we expect it to be tall. It has an amplitude of 3. So instead of going up 1, down 1, it's going up 3, down 3. And then the positive 3 on the end, oops, sorry about that. The positive 3 on the end represents the fact that it is going, that it is being shifted up 3 units. So rather than being centered on the y, on the x-axis, it's being raised. So for an example, if I can kind of show you a little bit, if it was just 3 sine of x, I would just be going up 3, down 3. But with it being that function plus 3 on the outside, it means we're actually shifting this up 3 also. So it's no longer centered on the x-axis. So that's an example of the types of matching and identification that that we like to practice with today's lesson, is being able to, you won't have to actually sketch the graphs according to an equation, but you will need to know what the different values in the equation mean in order to match them to a specific graph. So let's look at the next page. Is part of your homework, where I would like you to take a look at this and match these equations to these graphs. I'd like you to just use your chart and the examples we've looked at to just kind of do a process of elimination and match those graphs. And then the next slide shows you your homework, which is page 327, 73 through 76, where it does entail looking at a graph of cosine and filling in the A and the D values that would produce that graph. So again, we're aware that this is a lot for digital learning, but review your notes, fill out the guided notes, and give homework a try, and we will discuss it hopefully when we see you back at school again on Thursday. Thanks, girls, and stay safe and warm. Bye.